who ran in the morning today? Me. Taiwan. Okay, ready? Yes. Today's topic heat exchangers. Most commonly used heat exchangers in industry share as two type heat exchangers. We'll talk about heat exchangers. Yeah? You know heat exchangers? Share as two type heat exchangers using R12. What is R12?
Refrigerant?
Hmm?
Is it a refrigerant?
Refrigerant, yes, coolant. R12 is called freon gas. Freon gas. Have you heard of freon gas? Okay. Where is freon gas used?
Cars.
Huh?
In cars.
In car airbag? Oh yeah. Freon gas is used in car airbag, yes. Where else? Freon gas is also used as a refrigerant. Not anymore, it's banned. Eh? It's banned. Looks like restaurant of why it's banned.
It's bad for the ozone.
Ozone, eh? Because of ozone depletion. Montreal Protocol 1985, Kyoto Protocol 1997, we agreed to ban to produce freon gas anymore. At that time we had ozone depletion. Freon gas was the major contributor to ozone depletion. We banned, then ozone will recover. Now we don't have any problem with ozone layer anymore. But the main reason was the ozone depletion problem. We banned, but the specific cases still use freon gas, like the car airbag and submarine and fire extinguisher retardant. Okay. We look at heat exchangers using freon gas and ethylene glycol. What is the main use of ethylene glycol? Anyone?
Cooling?
Coolant, right? Antifreeze agent. You put in your car antifreeze agent as coolant, ethylene glycol. Okay? So description: ethylene glycol is our product. Okay, we produce ethylene glycol as a coolant for car. So ethylene glycol is produced, but it's too hot. We just produced. The temperature is 370 K. It's a little hot. 370 K, close to like 97 degrees Celsius is hot. We need to cool down. We want to cool down this hot ethylene glycol from 370 K to 315 K. How can we cool down? We can use cooling water. In this case, we use freon gas. So we use freon gas as coolant. Difluoromethane, now the word freon gas, as a coolant or as a refrigerant, which is available at 250 K. A typical shell and tube type heat exchanger is used for this system, and the plant engineer recommend using carbon steel tubing with a pressure drop not exceeding 5 psi for either the shell or tube side. When you design shell and tube heat exchanger, controlling pressure is very important. And in this case, this plant engineer recommend, control the pressure drop not to exceed 5 psi. Okay? So we have shell and tube side input, tube side output, shell side input, shell side output. We see the difference between input and output. And then we are looking at the pressure drop. The pressure drop between this input-output flow should not exceed 5 psi. If pressure drop is higher than 5 psi, what do you think it will happen? Right? Oh, yeah?
It's going to burst.
Burst? Burst is too extreme word. What do you think will happen? It's called vibration. Vibration happens. Okay? When you operate the shell and tube heat exchanger, vibration happens. It simply ruins, not the burst, but it ruins the shell and tube efficiency, and eventually it will kind of break the bursting. Yes. So pressure control when you design a shell and tube heat exchanger is very important. Okay. Anyway, in this case, we should design not to exceed 5 psi pressure gravity. And when we talk about shell and tube heat exchanger, we know about heat duty or heat transfer rate is equal to UAF, log mean temperature difference. So U is overall heat transfer coefficient, A is heat transfer area, F is correction factor, and log mean temperature difference. How do you get log mean temperature difference? As you can see, we look at the input temperature, output temperature, from shell side and tube side. Shell side, tube side is top temperatures. And then the equation is given in how to calculate log mean temperature difference. If you look at this figure, a typical shell and tube heat exchanger used in industry, as you can see, shell is the container or vessel container. We have like input here, shell input, and then if you look at inside, this is called tube bundle or tube bank. We say tube bank or tube bundle. As you can see, we have many tubes, about 54 tubes maybe, right? And if you look at here, this one is called baffle. But anyway, this is typical shell and tube heat exchanger. If you look at this diagram, it shows main parts of the shell and tube heat exchanger. As you can see, we have shell side inlet, shell side outlet, tube side input, tube side output. You will pay attention to this diagram. Okay, so we have tube side input stream flows and tube side output stream flows. And then if you look at here, as I said, we have baffles. Especially baffle design is very important in shell and tube heat exchanger design. We call baffle spacing, means between this one baffle, 2, 3, 4. In this diagram, there are 4 baffles. Baffle spacing is a distance between these baffles. And baffle opening, one is called baffle curve, is the opening, okay, ratio opening compared to the shell diameter. So when we say baffle opening or baffle curve, we use percentages. But if you look at this one, we have baffle design. There are 4 baffles for baffle design. We have baffle opening. As I said, baffle spacing and baffle design is very important. Can anyone tell us why? What's the purpose of installing baffle?
To ensure mixing.
To ensure mixing, I like it. Okay, you can see this diagram. Why we install baffle? If we do not install baffle, shell side flow will all flow bottom, which is not good. Main reason installing baffle is to make the shell side fluid a little more turbulent. You can imagine. So we install baffle, so this flow goes bottom and top, make a little turbulent, trying to make that the shell side fluid encounter every fluid from tube side. So baffle design is important, as I said, spacing and opening. But the main purpose is to make little more turbulent flow for shell side flow, so that we can increase heat transfer rate between shell side fluid and tube side fluid. Makes sense, right? Okay. Now in this case, okay, shell side fluid only meet one time to tube side fluid counter current flow is called one pass shell and tube heat exchanger. Next diagram, simple. Tube side fluid in and then turn around and then come out this side. So the tube side fluid meet twice with the shell side fluid is called two-pass shell and tube heat exchanger. Okay? And then, as I said, the definition of a baffle curve or baffle opening is that the empty space, the other is blocked. It's kind of buried, right? To block the shell side fluid. Only shell side fluid flows through this opening, and then we represent Helper curve as percentage. And factors for fluid location, shell or tube side, very important. Which side you are going to use for your fluid. For example, if you are dealing with a fouling fluid, usually you can choose tube side because mechanical cleaning is easier. As we said, from the figure, we have two bundle or two bag. It's easy to take out from shell, and then we can do mechanical cleaning. So you are dealing with fouling fluid, then you can maybe choose tube side so that you can clean more often. Because as I mentioned, those two bags you can take it out to clean. If your working pressure is very high, you are dealing with high pressure, maybe you can choose tube side. In this case, the reason is to reduce the required wall thickness of shell side. If you are dealing with high pressure, means if you are using shell side, then we have to make that shell side safer. Maybe we have to increase the thickness. It will be more costly. So if you are dealing with high pressure, then you can choose tube side flow. You are using corrosive fluid, okay, same thing, tube side, to reduce the cost of the shell material. You are dealing with high viscosity or low flow rate. In that case, high viscosity fluid, low flow rate. You can choose shell side. As we mentioned, we can do the head-pull spacing, head-pull opening. You can design those things. Okay, head-pull spacing sometimes like 2 inch, 4 inch, 6 inch standard, 1 foot possible. But anyway, you are dealing with high viscosity fluid, low flow rate. Maybe you can choose shell side to obtain high heat transfer coefficient. And when we make the equation for heat duty or heat transfer rate Q is equal to UAF logarithmic temperature difference. In this case, this F correction factor. How do we get this F? Or you can use this diagram. The y-axis is correction factor F. And we have two parameters here, it's called R and P in this case. And if you look at the right hand side diagram, you can see shell side input temperature and shell side output temperature, tube side input temperature, tube side output temperature, lowercase, uppercase difference. You use that temperature difference or temperature profile to find the parameter P, parameter R. The parameter R is the pink color line. Okay? By using the parameters, you can get correction factor. Anyway, our objective today is to simulate shell and tube type heat exchanger. Okay? So as you can see here, we have our product, ethylene glycol. Ethylene glycol, which is hot, 370 K, and then available at 3 atm. High pressure. High temperature, not that high pressure, but high temperature. But this is too hot, so we want to reduce to 315 K. What do we use? We use some refrigerant or coolant. In this case, we use R12, freon gas, which is available at 250 K and 8 atm. What is the mass flow rate? 12,000 kilograms per hour. Okay? And given information here is a temperature profile. For example, ethylene glycol, EG is ethylene glycol. Ethylene glycol input temperature 370 K, output 315 K. R12 input 250 K, output 300 K. So temperature profile is given. Okay? We have to meet that demand for temperature profile. What is unknown? What we are looking for here? Now simply we are looking for ethylene glycol flow rate to meet this temperature profile. Make sense? Okay. We are looking for ethylene glycol flow rate. So far we have done mass balance. We did some design spec, we did some mass balance. Today we will do energy balance. Okay, so little different thing is we will still use the design spec to find out how much ethylene glycol flow rate to meet the temperature profile, we will use design spec and energy balance. Make sense? Okay. Our actual process flow sheet will be look like this. A little different than the previous one, but this is very interesting practice. We will design two different approaches for shell and tube type heat exchanger. You can imagine if you look at the top side of this one and bottom side. So we have two different approaches for shell and tube heat exchanger design. And the top side design, we will use a simple heater and cooler to design shell and tube heat exchanger. Bottom one, we will look at it shell and tube type heat exchanger. Okay. So in Aspen, we have a heater, cooler unit block. We also have shell and tube heat exchanger unit block, a different unit blocks. We will use those different unit blocks to design shell and tube heat exchanger. Then what is the advantage of using this top design? John?
You can change
So we have two different approaches. Yes? Yes or no? Yes? Okay. We can design shell and tube using this top design. We can use shell and tube heat exchange type design or bottom design. My question was, what is the advantage or main use of this top design for shell and tube heat exchanger? You can guess. More simple. Well, I don't know whether it's simple or not, but good guess. Simple. Anyone? Anything else?
cheaper.
Cheaper? Oh, cheaper. I don't know whether it's cheaper or not. We can do economic analysis, But, well, I don't know. Anything else?
More product,
More, huh?
like higher mole fraction.
Higher mole fraction, I don't think it will affect the mole fraction or
Efficiency?
mole flow. Huh?
Efficiency?
Huh?
Efficiency?
Efficiency, maybe relevant to efficiency, I guess. Okay? This top design is very useful between factories. Okay? For example, we have refinery. Refinery requires a lot of heat. Don't you think so? We run a lot of distillation, column separation process. Refinery requires a lot of heat. Yes? If you build your own factory beside the steel manufacturing factory, they produce abundant heat, excessive heat. They simply waste all heat produced during the steel manufacturing process. That's the reason. When you build some refinery or chemical processing plant, you build very close to some other factories around. That's why we call complex. Of course, it requires a lot of water. So water resource is very important. But you build your factory very close to some other factory. For example, if it's a refinery very close to steel manufacturing factory, you can get that heat free. You understand? This design is good for that. Okay? Between factories. Then how about bottom one? What do you think now you can guess? Huh? Look, come on.
Single factory?
Single factory, within factory. Have you been to Thailand milk processing plant? Or
Yeah.
15th Street?
Driven past it.
You just passed, you never did the tour there, plant tour, not there. If you go milk processing factory, we have Highland Milk Dairy Factory on 15th Street, South Factory. Yeah, Highland Milk Processing Plant. No? Anyway, we have a milk processing plant. Within factory, you use this kind of heat exchanger. Shell and tube heat exchanger, right? Within factory. Between factories, you can use this type heat exchangers. Make sense? Why? In this case, the pipeline length will be like 1 kilometer, 2 kilometer, doesn't matter. Okay? That's the reasoning. But anyway, we look at these two different design approaches to model or simulate heat exchangers, especially shell and tube type heat exchangers. Any question? No questions. No questions. Good. Let's go. Specialty chemical is metric unit.
For you.
Come on, help me. Components.
Ethylene glycol.
Ethylene glycol.
R12.
R12. Yes, huh? R12. Yes. If you go methods, NRTL fine, or binary interaction parameters, okay? Estimate missing parameters by unit vector. Alright, table generation completed. I go simulation in domain. Very simple. Yes, what we are looking at today. So if you look at here, we are working on exchangers. Exchangers. We have 4 different exchangers. The first one, heater or cooler. Second one, shell and tube type heat exchanger. Third one is called multi-stream. If you have more stream than 2, like 3, 4 output stream, you can use multi-stream. And this one, if you want to do some heat transfer calculation, you can use this plugin. Okay? But we are going to use this one and this one today. As you know, I use a duplicate to facilitate our process. So I will duplicate our input streaming simply. Now we have one heater. Let me install one heater here. Okay? Let's connect step by step. Little pay attention, please. So let's name it. This one, let's say R12 input streaming. Okay. This one, I used to duplicate, so it's also R12 input stream, but I name it 1. This is the heater. This is R12 out. Let's go up to here. Only go further. Okay. Now we are working on R12 input stream. Okay. It's given R12 input stream is given 250 K, 8 ATM, and 12,000 kilogram per hour. Now our default temperature is degree Celsius. Of course, you can choose drop down arrow. You can choose Kelvin, or you can define or specify your own unit. Okay. So if you go, please follow my mouse cursor. Left top menu bar, there's for unit. You can click unit set. You can specify your own unit set to use. Okay? Copy from SI unit, metric unit, English unit. There are different copy from SI unit. You can choose unit you want to simulate. Maybe I can choose kilogram hour, Kelvin, pressure, ATM. Okay? And heat, watt, kilowatt maybe. You can specify your own unit to use. I defined US-1. So go to drop down arrow. You can choose US-1. Now you can use your own unit. Very useful tooling. Now we are working on R12 input stream 250K. Pressure is 8 ATM. R12 is 12,000 kilogram per hour. We are working on heater, and heater means how can we find out this temperature pressure? Heater, you can look at it output stream temperature pressure from the heater. So I can look at it output stream R12 was 300 K, and what information is given? Pressure drop should not exceed 5 psi. So I can use that information, Lucia. So what should I type in? Wonderful! Negative 5 psi or negative 0.34 atm, either one. Yeah? Pressure drop not to exceed. So I use negative 5. Okay, okay, let's do simulation. No warnings, no errors. Let me highlight it. Always I highlight it. What we are interested in? We are interested in temperature profile. So let's do temperature and pressure. Okay. So little pay attention here. We have to meet our temperature profile. Input is 250 K. Output is 300 K. The pressure is given in 1 digit. If I give you little information, follow my mouse cursor. It's called stream result. There's a drop down arrow very right bottom corner. If you click that one, you can set maybe temperature 0F, pressure 0.02, 2 decimal point. Then you can look at pressure in 2 decimal point. So our pressure drop is 0.348 atmosphere. Make sense? Now, after run, always check your result. We used the heater. Now, as you can see, R12 input temperature is 250 K, output temperature is 300 K. What does that mean? It absorbed heat. Right? It absorbed heat. How much heat? So little pay attention. We do energy balance, especially heat play. So if you go heater, result, R12 freon gas absorbed about 180.049 kilowatt of heat. That's why the temperature increased from 250 K to 300 K. Make sense? All right, makes sense, of course. Now let's add our ethylene glycol flow. So I will use manipulator, duplicate, okay? And then we use another heater, but we can design as cooler, as I said. And let's connect material. I don't like that arrow flow, so I will flip, rotate icon, flip horizontal, rotate icon lightly, flip horizontal, then I can connect or swing. We are looking at ethylene glycol stream, so I'll name it EG, input stream. This is a duplicate. What to duplicate? We duplicate this input stream. I will name this one EG input 1. This one is for cooler, and this one EG out on stream. Don't know what to do, maybe go next. We are working on ethylene glycol input stream. Temperature is given 370 K. That's our product. Ethylene glycol is our product. Very hot. Pressure is 3 atm. How much ethylene glycol? Page. You're looking.
That's what we're trying to find.
That's what you're trying to find, wonderfully. That's what you're trying to find. By looking at energy balance. Initially, what do you know? When we design heater, Freon gas stream, heat required was 180.049 kilowatt. So you remember that value. Okay. Now we are looking for how much ethylene glycol flow rate is. We don't know. Brian, then what do you think we must do?
Total flow rate.
Huh?
Use the total flow rate.
Total flow rate. Yeah, okay, total flow rate. So what do we need to do? You don't know. Anyone? Dylan, what do you think we need to do? You don't know. Who can rely? Cannot answer always correct.
We need to do a design spec for it.
But right now, what do we need to do here? You cannot tell.
Yes.
Type.
Did you
Yes. 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 Please. Is it difficult to guess? Put any number. I'm talking about. Just put any number here. Why? We don't know. We are looking for. Put any number and then come back to design spec sensitivity analysis. Find out what the exact value will be. Make sense? Don't be afraid of guessing. Or don't be afraid of making a mistake. Just do. We don't know means put any number. You want to put different number here? No problem. Yes. Let's go. We are working on cooler. As I said, you can get output stream of ethylene glycol. That's the information we can put here, which means 350 K pressure drop should not exceed 5 psi. Okay? I think that's all. Now, the question is, okay, if you look at here, initially heater, let me show you again, heater absorb this much heat, 180 kilowatt. Yes? We used 5,000 kilogram per hour of ethylene glycol. Let's look at it. How much heat? Negative 188.33 kilowatt. Jared, what does the negative value be?
He is leaving.
What? He is leaving or he is extracted, right? He is lost or he is extracted, he is leaving. Negative value. Okay? When we were designing heater was positive value. We are designing cooler, negative. Heat is leaving, extracted. Simply, ethylene glycol fluid losing heat because we want to cool down. But to do energy balance, Natalie, that heat duty should be what value to do energy balance? Huh? Equal to the heater value should be negative 180.049. Then, if we do the energy balance, then this temperature we may meet the output temperature 358. Right now, currently, we used 5,000 kilogram per hour of ethylene glycol. Okay, how much heat is extracted? Was about 188.33 kilowatt. Okay, as I mentioned, if I connect these two streams, okay, let's say steel manufacturing, we want to connect this heat to cooler. We will see clearly now. So if you go here, we have material flow, we have heat flow. I can connect using heat flow. So if I connect this heat, it will make more sense to you. So I transfer this heat. We used initially 5,000 kilogram per hour ethylene glycol. Remember that? Okay. Now I transfer heat from this cooler to heater. What do you expect after I connect? If you can answer this one, you are totally understand what's going on. Okay. So little pay attention to our temperature profile today. Yes? Okay. Now, we are focusing on energy balance, but how we can do the energy balance? Our target is to find out how much the ethylene glycol mass flow rate will be to do the energy balance. That's our question, you see. But we don't know how much ethylene glycol is necessary, so we guessed. We used the initial guess, 5,000 kilogram per hour. After we used 5,000 kilogram per hour, the cooler we look at how much heat is extracted was negative 188.33 kilowatt heat. Yeah. So from this cooler, how much heat is transferred is 188.33 kilowatt. When we design firstly this heater for fuel gas stream was 12,000 kilogram per hour. Yes. And then we look at it, how much heat is absorbed was 180.049 kilowatt. Make sense now? Okay. Let's transfer that heat from this cooler or ethylene glycol fluid to freon gas fluid. So we connected this heat by heat flow. If I run the simulation, what do you expect the result will be? Anyone? Yeah.
We'll need less energy over here from other sources.
So what do you observe? If I run the simulation, what do you think you will observe, or what do you see the difference from current condition to after simulation condition?
Will the duty be the same between here and
Right now, duty is not same. That's the reason. Right now, duty is not same. So you remember, here was negative 188. Here was positive 180. Come on, quickly. One time.
so last year will be more?
Wonderful. Brian, can you speak out and rephrase?
The horizontal downstream will be heated more.
That means this temperature will
Increase.
increase. Yeah? Make sense? Let's try. Come on, let's try. Wonderful. See? Finally, we got correct answer here. So no warning, no error. Didn't increase much. Initially it was 300K. Right now 302. Let's say if I increase ethylene glycol fluid, initially I just guessed, can we put 6,000? What do you expect? Come on, tell me quickly. Harder. Let's look at it. How harder? 305. If I put here, let's say 4,000, 3,000, 4,000. What do you expect?
Temperature goes down.
Come on. Lower, 292. But what is given? This temperature should be 300. This temperature should be 315. Yes? How can we do that? You use the design spec, find out the correct amount of ethylene glycol flow, mass flow in this case, to meet the temperature profile. Make sense? Okay, then let's do design spec. Because right now, this is how much? 4,000. We guessed it, we don't know the exact number. But we can find the exact number by doing design spec. But as I said, what we use? We do energy balancing. So I do design spec for energy balance. So this define, maybe I can define Q duty. We use heat. Q duty, heat duty is a block variable. Okay? So that's the block variable. And we are looking at ethylene glycol fluid because we gassed ethylene glycol into stream. So that's a pull-up. And net duty, we are looking at duty, kilowatt. Good. I named the Q duty. What this target should be? Now if you can answer this one, Brian, can you answer what this target should be? Brian guessed well but doesn't understand completely.
315.
Oh?
315.
315, no.
180.3.
Oh!
Zero.
The 180.33 or something. The heat duty required to get.
Wonderful. 180.049. Weston, we are talking about this one?
Yes.
Half correct, half wrong. Still not correct. The number is correct.
Negative.
Come on, guess. Bailey, I can rely on. Wonderful. Did I fail you? Did I fail you? Somehow, Bailey, every time correct answer. Negative. We are designing cooler. Heat is extracted. Negative sign. So we should pay attention. This one it should be negative or positive. 180 is high number, so tolerance may be 3 decimal point accuracy. Yeah? Wonderful. Okay? What do we vary? Come on, quickly.
Ethylene glycol flow.
Mass flow of ethylene glycol. Yes, mass flow of ethylene glycol. So, component ethylene glycol. Initially, we guess 4,000, 5,000, 6,000. So, lower is 1,000, upper is 10,000. Ranging. Yes? Can I reset just in case? Let's look at it. Truly, how much ethylene glycol is necessary? No warning, no error. Make sure the output temperature is 300 K, 315 K. Correct? Now we can find out how much ethylene glycol truly necessary. So 4,780 to do energy balance to meet the temperature profile. Okay? It's easy. As I mentioned, this design is very useful for simulating between factories. Now, within a factory, we can do shell and tube type heat exchanger. So this is a shell and tube type heat exchanger. And we can still use the same input stream. So I can same input stream, output stream, same input stream, output stream. Okay. Let's name it this one. R12 input second stream. This one should be R12 output second stream. EG input second stream. EG output second stream. And this is for shell and tube type, shell and tube heat exchanger. Sensitivity analysis and design spec, there is a big difference. Sensitivity analysis does not affect your simulation, but design spec will affect your simulation. So if you leave design spec active, it will affect your simulation, so you have to deactivate it. Okay? So I want to go to the initial condition, but we have design spec, so I right click and deactivate. That's the difference. Sensitivity analysis does not affect your simulation. Design spec affects your simulation. So as long as the design spec is active, it will affect my simulation. I cannot go back to my initial stage. So I deactivate by right clicking, right click your mouse, and activate, deactivate, hide, rename, delete. Many functions are available. Okay. Let's go next. We are working on shell and tube type heat exchanger. we use shortcut. When you take lab 2, you will learn with the more rigorous shell and tube type heat exchanger. This is called shell and tube exchanger design and rating, EDRE. Design one course, we do shortcut. Okay, so shortcut is fine. There's 4 different calculation modes: design, rating, simulation, maximum power in. In lab 2, you will learn more about rating simulation. Design one, you will do design in. Okay, good. Specification, we can use hot stream outlet temperature or cold stream outlet temperature. I can use hot stream outlet temperature. Hot stream outlet temperatures should be 315 K. And if you go here, pressure drop tab, we know the information. So hot side, negative 5 psi. And if you drop down narrow, cold side also should be negative 5 psi. And if you go U method, overall heat transfer coefficient, you can use default, but if you overall heat transfer coefficient is given, you can choose constant new value and you can put the value. But now we can use the default value, no problem. Right now, the initial ethylene glycol input stream was 4,000. So you can imagine this output temperature. How possibly 315.3? What's going on? You see 5,000 or no 4,000? Maybe maybe I didn't reset. I deactivated the design one. I didn't reset. So reset, very important. Do not forget. Okay? Yeah? Freon gas output temperature, check. Freon gas output temperature should be what temperature?
Is it 370?
No. I am looking for output temperature, freon gas output temperature.
315?
3 good gas. Joe, can you help me? That's a good friend. No? Clear up. 300, should be 300, but it's 292. Yes? And then ethylene glycol output temperature should be 315, so it's correct. But this one should be 300, but it's 292. Why? Joe, you can answer now.
Flow rate of the EG.
Wonderfully, because the easy flow rate is 4,000, maybe not enough for the energy balance. Right? How can you find them? I have no time. I will go quickly. We can simply do design spec. Let's do design spec in this case. Let's do property set. So if I go design spec, I go new. Maybe we are looking for R12 output to temperature. This one should be 300, as we know. So that's the strings. Okay. And then I can choose stream variable maybe. Yes, stream variable. And we are looking for R12, R2 temperature. That's the temperature. And in K, so the spec will be, I am looking for R12, R2 temperature. That's the variable I name. And this value should be 300. Brilliant. Any question? No? Okay, 0.001. Brilliant. Then what do we vary? Mass flow, eh? Oh, wonderful. No. Okay, we are looking at EG input mass flow. Ethylene glycol. Okay, let's reset just in case. Run the simulation. Okay, first make sure our temperature profile, especially output temperature, ethylene glycol 315. So I can remove pressure now. Eh? So you can see pressure, temperature. We are increasing temperature. And freon gas output 300 K. So, okay, we met that demand. Now, if you go design to result, you will get the same result. Eh? We found out the ethylene glycol input flow rate. First approach we used energy balance. Yeah. And then second approach, we use the temperature profile to find out ethylene glycol input mass flow. Any questions? No questions? I am very nice, so your homework you can finish very quickly. Natalie, you finish your homework.